Okay. Good evening, everybody, and Happy New Year.
Happy New Year.
I'm here with John Curry and Gerald
Happy New Year.
McKeegan, and we can't think of a better way to bring in the new year than to talk about astronomy. So that's what we're going to do. And
Yeah.
it's, of course, a cloudy and rainy night. And this isn't just a virtual telescope viewing as a result, it is a virtual telescope viewing. So we are at our respective abodes with different background screens. Although, Gerald, it looks like you're actually showing us reality.
I am. I'm in the real world. You guys are in the
That's right.
virtual world.
Yes.
In fact, I'm in my daughter's bedroom. And,
Okay, that's pretty
and
good.
in fact,
Yeah.
behind me, you see here, that's my daughter's shot glass collection.
Ah,
everywhere she goes, she
you
collects them.
must be very proud.
Oh yes. Hey,
Yeah.
before we
I,
go too much farther here,
okay.
you were showing that slide of the Fremont Bank being a sponsor, and I just want to call everybody's attention to that. Fremont Bank has made a very generous donation to the Chabot Space and Science Center to support our STEM programming. Because of the COVID stuff, we are closed to the public right now, but we are still working. We're still doing a lot of programming, all of it online, and we still need your support. So, thank you to Fremont Bank. And if any of you would like to help us out, you can go to the Facebook page and click on the donate button there, or you can go to Chabot's website, chabotspace.org, and you'll see a donate button up at the top of the page, and you click on that and give us a donation. We would really appreciate it. We figure we're going to be doing this for a few more months and doing a lot of virtual programming. We've done over 80 virtual programs now, not only on the telescope stuff, but also science programming for schools and so forth. So any support that you can give us, we would really appreciate it. All right.
Cool. Very good. So, we're we're actually giving this presentation on a special day.
Yeah.
It's
Couple of
Perihelion.
things. Yeah.
It's Perihelion Day,
Yeah.
and
Yeah. I felt it.
yeah, I felt I got woken up by a jolt at 5:30 in the morning,
Yeah.
and at that moment I realized it must be perihelion. Gerald, why don't you talk about perihelion? You tried to explain something about it a couple of weeks ago when we started getting into this debate about the shortest days of the year,
Yeah.
and our eyes were crossing over. But at least
Yeah.
today is actually perihelion, actual perihelion. So
Yeah.
maybe we'll
Yeah.
do a better job explaining this.
Okay. Well, the Earth orbits around the sun. Some of you may know that. And the orbit is not a perfect circle, it's an ellipse. So it's kind of slightly oval shape. And because of that, sometimes the Earth is closer to the sun than at other times. And when it is closest, or I'm sorry, the Earth is closest to the sun than at other times. When it is closest to the sun, we call that perihelion. When it's farthest from the sun, we call that aphelion. So today, this morning at 5:31, it was perihelion. That's when the sun or the Earth was closest to the sun. Uh, and because of that, the Earth is moving faster in its orbit. And because of that, it takes a little bit longer for the Earth to make one complete revolution relative to the sun, one complete rotation relative to the sun, which means that although the days are very short, the daytime period is very short, the actual time it takes for the sun to go from one point in the sky all the way around to that same point the next day is actually longer than it is in the summertime. So that's what I was trying to explain the last time, and I'm not sure if I did a very good job of it. Probably.
It's a hard thing to explain only in words. It's one of those
Right.
moments where it'd be nice to have lamps and oranges and something
Right.
like that
Right.
to demonstrate
Right.
it. But
Really
Yeah,
fancy graphics.
yeah. The
Or a
important
swivel chair or something.
yeah, right. The important thing is that the seasonal day of the year, which is always associated with winter time, has nothing to do with aphelion and perihelion. It's the tilt of the Earth and the amount of time that the sun is spent uh, 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 visible in your part of the world. So it's winter here in the northern hemisphere and it's summer in the southern hemisphere, whereas perihelion and aphelion are more of the orbital characteristics of the Earth around the sun.
Right.
And it does have an effect on the actual length of the day, but not anything really to do with seasons.
Right, right. Yeah, there's a common misconception that, summertime for us here in the Northern Hemisphere, that must be when we're closest to the sun.
Right.
And that's actually not true. In fact, for the Northern Hemisphere summer, we're actually farthest from the sun. The aphelion is on around July, early July. And so we're actually farther from the sun than we are at perihelion, which for us is wintertime. So.
All right. Well, now that we've cleared up that whole mess, we can move on. So the other thing that I learned just yesterday was that this is the 220th anniversary. Not actually today, but this week is the 220th anniversary of the discovery of Ceres. And that's the first main belt asteroid that was discovered by Giuseppe Piazzi in 1801.
1801, yeah.
And
on January 1st, 1801.
January 1st, 1801. So he had a really busy New Year's, and he was very pleased with the result. So I do have a photo I want to share of that, and so bear with me here for a moment. And this is a stunning photograph taken by the Dawn spacecraft a few years ago. And here we go. Can you guys see that?
Yep.
All right. So it's a high resolution mosaic, actually. This is actually a whole series of photographs reassembled into a single photo of one side of Ceres. And the first thing that's quite stunning about this is just the resolution of the craters, the spherical nature of this minor planet, essentially. And of course, the mystery white spot right here in the center that everybody was wondering what that was when it got photographed. And there's been enough time to study the data that came back from the spacecraft and compare it to other data that has been gathered from other minor planets around the solar system. And what was realized is that Ceres is very rich in water. There's a lot of water in the mixed in with the contents of the rock. And also inside that water is brine, so it's a lot of salty water. And what happens is the water is forced to the surface, and the water then boils off, and what's left is salt. So essentially, this is a space salt lick. And so, like I was telling Gerald, it's all ready for the space cows for when they show up. And but that's what it is. At first, there was speculation that it was snow or ice, and how is the water just showing up in that one part of the planet? So it turns out it's salt.
So it just happens that the water there, or the salt, is reflecting sunlight perfectly back to the spacecraft at that point.
Right.
And that's why that's the only place that is lit up.
That's the most visible location for this phenomenon. And it also might be locally more concentrated there. That's another possibility. So anyhow.
This was actually one of several that they eventually found on Ceres, similar deposits like that. So.
Yeah, this one was just the most notable and caught everybody's attention. So, Gerald, I'll bet you got some more things to tell us about Ceres.
Well, you mentioned that it's the anniversary of the discovery of Ceres, so I thought I'd tell you the story about the discovery of Ceres. So if you'll bear with me here for a second, I'm going to share my screen. Got a little PowerPoint here that I'll show you. And let's see if I can get it launched here. There we go. So this is another view of Ceres, also by the Dawn spacecraft. The Dawn spacecraft actually orbited around Ceres for quite a while. And I just wanted to tell you the story of how it got discovered. Ceres is it kind of has two different designations. It's an asteroid in the main asteroid belt, which is between Mars and Jupiter. It's also a dwarf planet. It meets the criteria for the dwarf planet. That criteria was established in 2006 by the International Astronomical Union. So I thought we'd just go back a little bit in time into history and learn a little bit about how it was discovered. So we'll go back to around the middle of the 18th century. At that time, only 6 planets were known: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. And astronomers by the mid 18th century had calculated roughly the distances between them. And they realized that there was a kind of a pattern for the first 5 or 4 planets rather, but then there seemed to be a gap between Mars and Jupiter. And several astronomers in those days attempted to come up with some sort of a mathematical relationship that would explain that the spacing. And eventually a guy named Johann Titius published in 1766 a formula, if you will. It's kind of a normalized number sequence. What he did is he took the distance between the sun and Mercury, divided it into 4 parts or 4 units, and then expressed all the distances of the planets based on that 4-unit distance from Mercury. So Venus would be 4 units plus 3 units. If you double 3, you get 6. It turns out Earth is at 4 plus 6. If you double 6, you get 12. Mars is at 4 plus 12. And then there's kind of a gap. And then you have 4 plus 48 is the distance to Jupiter, and 4 plus 96 is the distance to Saturn. So you got this nice pattern here, except that there's a gap between Mars and Jupiter. And the one between Mars and Jupiter would be where you'd expect to see a distance of 4 plus 24 units. And possibly there would be others even farther out. The next one out, if you follow the same sequence, should be 4 plus 192. Titius published this. Titius was just a quiet guy who, did a lot of math and things, and he came up with this idea. But there was another astronomer. His name was Bode. And Bode was, he's a very popular guy. He was an astronomer. He taught astronomy. And he published a astronomy textbook. And in it, he included a reference to Titius's sequence. Now, like I say, Bode was a very popular guy. He was also a bit of a loudmouth and a self-promoter. And he really pushed the idea that this mathematical sequence was valid for all of the planets. And because of that, there has to be a planet between Mars and Jupiter, and there has to be another planet beyond Saturn. And both of those should follow the same numerical sequence. So, he pushed that idea so much that he no longer was referred to as Titius's law. It became known as Bode's law. So he kind of co-opted it. Nowadays we call it Bode-Titius's law, but back then it became known as Bode's law. And it's predicted that there should be a planet between Mars and Jupiter, and it should be one beyond Saturn. And so everybody was very interested to see if that would hold true. In 1781, William Herschel, who had a very good telescope, accidentally found the planet Uranus And when they calculated the distance to Uranus, it turned out it met the criteria. It corresponded to that 4 plus 192 distance from the sun. So it looked like this sequence was valid and it should work. And that meant there had to be a planet between Mars and Jupiter, and they just needed to find it. So a number of astronomers began searching for it, one of whom was this guy here. His name was Baron Franz von Zach, and he had a fairly good telescope, and he began searching frantically, trying to find that planet between Mars and Jupiter, and he just had no luck at all. So he was a fairly prominent guy, and he got together with a few other astronomers in September of 1800, and they decided to form what they were going to call the Celestial Police. And their plan was to find this planet. And the way they were going to do it is to divide the sky up into 24 sections. And then they were going to assign each section to a different astronomer in Europe. Now, they didn't ask the astronomers if they wanted to participate. They just decided they were going to make this assignment, and that would be their project for the following year, 1801. Meanwhile, there was an astronomer. He's actually one of the ones that they were going to make this assignment to. His name was Giuseppe Piazzi. He was an Italian monk, and he was also an amateur astronomer. And he was busy. He had another task that he had assigned for himself for 1801. He'd actually started it earlier than that. And that was to create a new, more accurate star catalog. And his methodology was to point his telescope at a part of the sky and then very carefully plot on paper the positions of all the stars in the field of view of his telescope. And then he would come back the next night and look at the same field of view and confirm that he had correctly plotted all the positions. Well, he did this for a field of view in the constellation Taurus. And then the next night, on January 1st, 1801, he looked again and he discovered that one of the stars in the field of view had moved quite a bit. And he was not sure what he was seeing. He actually thought maybe it was a comet. And so he continued to observe it every clear night from January 1st through, or not every clear night, but just about every clear night from January 1st through February 11th. After February 11th, he got a little sick, so he couldn't observe anymore. And besides, Taurus had gotten so far over into the western sky that it was in the sunset. And so it was very hard to see stars or faint objects. So he really couldn't observe this object anymore after the middle of February. So he sat down and he started trying to do some math and figure out what the orbital elements were. But in the meantime, he sent a letter to Boda. And he said, well, I've got this object that I've seen. You know, it could be a comet, but I suspect it's something a lot better. So he didn't come right out and say it's a new planet. He just said, yeah, maybe. Well, Boda, being a self-promoter and never missing an opportunity to get his name in the newspapers, immediately said, this is it. And he put up the mission accomplished sign and said, you know, we have succeeded in finding that planet between Mars and Jupiter. You know, the orbital elements actually hadn't been determined yet. The orbital elements are a set of numbers that describes an orbit, including how far they are from the sun. And Piazzi really hadn't been able to figure it out yet. But Boda went ahead and declared mission accomplished, and away they went. And so Piazzi decided to give the object a name. He initially gave it a very long name, but eventually he shortened it to just Ceres. So after that, Piazzi continued to observe this Ceres and tried to calculate the orbit. Eventually, he came up with an estimate of the distance from the sun of about 2.7 astronomical units. Now, 2.7 astronomical units means it was 2.7 times the average distance between the Earth and the sun. And that distance agreed with the 4 plus 24 sequence that was missing in Titius's sequence. And so it looked like, yes, indeed, they had found a planet between Mars and Jupiter that conformed to Bode's law or Titius's law. Unfortunately, by the end of February, he couldn't observe Ceres anymore because it was too far in the western sky. So then it was a matter of continuing to try to calculate an orbit to figure out, where is it going to be and when can we find it again? His calculations were not accurate enough though for him to actually predict when they would be able to see Ceres again and where they would be able to see Ceres again. Piazzi just wasn't that good of a mathematician. But at about the same time, there was a very talented mathematician, and his name was Carl Gauss. And Carl Gauss was actually relatively young at the time. He was in his mid-20s. And he used Piazzi's data to calculate the orbital elements for Ceres and predict when and where they should be able to see it again. And he gave that information to a number of astronomers, including Baron von Zach. And von Zach was able to rediscover Ceres exactly where Gauss predicted on the last day of 1801. So almost exactly a year later, it was rediscovered. And interestingly, the methodology that Gauss developed had never been done before. No one had ever taken data from an object that was in orbit and used those data to calculate the orbital elements and determine where an object would be at some later date. And Gauss's method was so accurate that they continued to use it for many, many, many decades. In fact, some people still use his method for calculating the orbital elements for newly discovered asteroids, even today.
So Gerald, when Carl Gauss first delivered that data, did they call it a Gaussian distribution?
No, that was part of Gauss's other work. He was a brilliant mathematician. He was, when he was like 6 years old, he was already solving complex math problems. So the guy was, one of those brilliant individuals.
Well, he was the father of modern statistics.
Yep. So anyway,
hey, Gerald.
Yes.
Gerald, when Piazzi first named Ceres, you said there was a different name, and one of our people on Facebook here wants to know what that name was. Do you have the full name?
That's a good question. I don't remember what it was, but it was a longer name. It included the word Ceres, but it was a longer name. They like to name things after people and give them honors and so on, and eventually they shortened it. Nobody wanted.
I got it. I found it. It was Ceres Ferdinandea.
Wow.
There you go.
after the goddess Ceres, Roman goddess of agriculture, Ceres in Italian, who was believed to have originated in Sicily and whose oldest temple is there, and combined with King Ferdinand of Sicily.
Well, I'm glad he shortened it down then. That's
I am too.
Mouthful.
Yeah, absolutely.
So anyway, they like I said, they put up the mission accomplished sign, and that's always a bad sign. So problems began to develop, and then the first problem was something that was noted by William Herschel. Again, William Herschel had one of the biggest telescopes. In fact, at one point, I think he had the largest telescope in the world, and he attempted to measure the size of Ceres. and he just couldn't get it resolved enough to where he could measure a size. It just was a dot in the sky. And so that became an issue. If it was a planet between Mars and Jupiter, they ought to be able to see it at least as well as Mars, but they couldn't. It was just too small. And then another problem came along. A guy named Olbers discovered yet another object out in about the same distance from the sun, orbiting roughly the same orbit as Ceres. And it too was too small to measure in size. So now you had two objects out there orbiting around the sun in the same distance, too small to be a planet. So what the heck are they? Gauss had a kind of a derisive name for it. He called them just clods of dirt, and didn't feel like they warranted any other attention. But others, continued to try to theorize what they were seeing and what else they might see out there. Olbers later on came up with the idea that these objects were actually part of a planet that had broken up. And for a long time, that was the belief. In fact, although it is not true, it is still a common belief even today that the asteroids in the main asteroid belt are part of a planet that was once there but somehow broken up. That was disproved quite a while ago, but some people still believe it. So Herschel came up with a new name. He decided to call them asteroids. And the word asteroid means little star. And when you see them, in fact, I'm going to show you a little short sequence of images later on here, and you'll see why they call them that. They look like stars, except that they're moving. Okay, so not long afterwards, things began to progress. More and more asteroids were found. In 1807, Vesta and Juno were discovered, again, orbiting the sun at about the same distance. By 1850, there were 10 asteroids known, all of them in the main asteroid belt. 2 years later, they had found 11 more. And, they continued to find more and more asteroids. Now, again, there was this theory that they might have originated from a planet that had broken up. If that was true, all these asteroids, when you calculate their orbits should all intersect at one point called a node. And when they calculated the orbits, they could not find any evidence that their orbits intersected at a node. So by the late 19th century, the idea that it was a broken up planet had pretty much been tossed out. It was a nice theory, and some people hung on to it, but most astronomers no longer believe that that's what the asteroid belt was. In 1890, by 1890, there were 300 asteroids known, and the number was increasing almost every year. In fact, it was increasing so much that a lot of professional astronomers didn't want anything to do with asteroids anymore. And by 1890, astronomers were now putting cameras on telescopes, and asteroids were not welcome. When you took pictures, especially back then, you took pictures with a camera on a telescope. You had to expose the camera for a long period of time, anywhere from several minutes to over an hour. And that's the only way you could get good images of those deep sky objects, those faint, fuzzies out there, the galaxies and nebulas and so on. And it was really frustrating to have an asteroid wander through the image and create this streak that kind of messed up your image. So a lot of professional astronomers decided they didn't want anything to do anymore with asteroids, and they came up with some pretty derogatory names for them, the most famous of which was vermin of the sky. And someone else called it the plague of minor planets.
That sounds much more recent, the plague of minor planets.
Actually, that was another 19th century guy.
Was it?
Yep. So anyway, it was, it became a subject that a few astronomers studied, but most of them didn't want anything to do with asteroids by the 20th century, until they started realizing that some of those asteroids came very close to the Earth. So today, we know of a lot more asteroids. We have found more and more and more. In fact, today, there are over 1 million known asteroids orbiting around the sun. Most of them are between Mars and Jupiter. Some of them come close to the Earth as near-Earth asteroids. And we owe it all to Mr. Pleiades on January 1st of 1801. All right. Oh, I had one other thing I wanted to share with you.
Yeah, you had an animation, I think.
Yeah. Hang on here. This animation is just going to show you, I hope. That's not it.
No, wrong one.
That's the wrong one. There it is. Okay, so this is what asteroids look like through a telescope. This is an asteroid. These images were taken over about an hour-long period of time. And there are actually 4 images, and you can see the asteroid. Hopefully everybody can see it right there. They move across the sky, and you don't see any detail on them. All you see them as is a little dot. Now, this sequence of images was taken by our telescope at the Chabot Space and Science Center, our 36-inch telescope. So this gives you an idea of what Pleiades was seeing when he was looking over that period between January 1st and February 11th of 1801. All right.
Yeah,
I bet you he didn't have a 36-inch telescope.
No, he didn't. Quite a bit smaller.
Yeah.
All right.
Well, it was all, at that time period, the telescopes were not very good. It's actually, pretty remarkable that
he saw anything.
Right. And was able to compare it over multiple nights and all of that. That's quite remarkable.
It is.
Right.
Right.
So Richard, speaking of things flying around in space, tonight, had it been clear, we would have had an opportunity to see the Quadrantid meteor shower. The Quadrantids is a modest meteor shower that happens every year about this time. It comes from an extinct comet that was discovered in 2003. And if we had clear skies tonight, we'd be able to go out after midnight and actually see the Quadrantids. I've got an image I can share with you. You've actually already seen it because I messed up a couple of minutes ago, but let me try again.
That's all right.
And here you go. This is looking towards the northeastern sky about 2 o'clock in the morning. You see the Big Dipper here. Down here is the star Arcturus, and the Quadrantid meteors will appear to come from a point right in this area here. Now, this area used to be called Quadrans Muralis, I believe it was. It was a constellation that had been named a long time ago. They have since reorganized the night sky, and that constellation doesn't.
It's an obsolete constellation.
Right.
Yeah, it was named by Jerome Lalande.
There you go.
Yeah, French astronomer.
I didn't even know that. So anyway, the meteors are named after that defunct constellation. So they're called the Quadrantids, and they happen every year around the 2nd or 3rd of January. And they're happening tonight. So if you happen to be somewhere where there's a clear sky, stay up after midnight around 1 o'clock in the morning or so, look to the northeast. although actually you can look in almost any part of the sky, but the meteors will appear to be coming out of the northeast. The point that they appear to be coming from is called the radiant. And the reason for that is because that's the direction that the Earth is moving in its orbit around the sun. So we are moving in this direction tonight, and we are passing through a stream of particles left behind by what is now an extinct comet. And as we pass through them, they appear to be coming at us from this direction, but it's actually we are flying into it in that direction. And that's how we get a meteor shower.
There's actually a competing theory on that. You know Peter Jenniskens
Yes, I
from here in
do.
the Bay Area. So
Yes, I
Peter,
do.
yeah, I'm lucky to have met him. He's a real interesting guy, and he's one of the experts in identifying the sources of meteor showers and what comet was it, what asteroid was it. He has the theory that it's an asteroid 2003 EH1 that causes the quadrantids and not a comet. But there's also another theory that 2003 EH1 isn't an asteroid at all, but is in fact the center, an extinct comet.
Yeah,
so there's some confusion on what the actual source is. It could be one or the other.
Right. Well, one of the misconceptions is that there are comets and there are asteroids and never the twain shall meet. But in fact, there's a continuum. A lot of comets, as they lose the ice on the outer part of the comet, and that ice is just replaced by the dust and rock that was embedded in the ice, pretty soon the ice is all interior, and the former comet now looks like an asteroid, but it's actually an extinct comet. And we think actually quite a few asteroids are extinct comets. So he could be right.
They could both be right.
They could both be right.
Both, yeah.
It's an asteroid, but it's actually an extinct comet.
You say potato, I say potato.
Right.
Cool.
All right.
So I hope that answers people's questions about the meteor shower, because there were a few.
Yeah, I think that covers it.
So if some folks are just coming in and they're wondering why we're not pointing our telescope and have a camera on the telescope, our telescope up at the Chabot Space and Science Center is in the rain right now. Actually, the telescope isn't in the rain. But
it's like, what, did you leave the roof open again?
Yeah, but the observatory is getting rained on right now, so we cannot open the telescope. So we're having to kind of wing it tonight here, and hopefully the weather will be better next week, and we'll be able to go back to putting cameras on telescopes and showing you the wintertime sky. Speaking of which, I think one of the things in the winter sky is the Pleiades. And Richard, didn't you have something
yes,
you wanted to talk about the Pleiades?
All right. Well, there's been a story that's been circulating in the last couple of weeks that captured my imagination and many other people's as well. There's kind of a new field of astronomy called anthropological astronomy or cultural astronomy, and there was a researcher who was speculating that the story of the Pleiades may actually go back way early prehistoric times, like 100,000 years ago, because the Pleiades is always a story of the seven sisters or seven stars, but one of the stars goes missing. And the story from Australia and the story from Africa and the story from North America and the stories from other parts of the world, all generated by cultures that never had any direct contact with one another, have remarkable similarities. And the most remarkable similarity being that it started out as 7 and then became 6. So if you look, I'm going to share my screen here for a second here. Let's see. Bear with me. There we go. Hit share. Okay, can you guys see that?
We can.
Yeah.
Okay, great. So this is, and thank you, John. John shared this photo with me earlier. It's actually out of Starry Nights, the
Right.
planetarium program.
Mhm.
And you could see the seven sisters here. There's Pleione and Atlas and Alcyone and Merope and Electra. And the ones to focus on right here are Pleione and Atlas, because if you were to go outside and look at the Pleiades, it would be very hard to distinguish these as two separate stars. They would look to your naked eye as one star. And you could see that in 2020, this is the relative distance between the two. And of course, this isn't that, these two stars are actually quite far from one another, but to us, they appear close together because they occupy the same direction in space. But 100,000 years ago, you could see that they're almost twice as far apart, with the rest of the stars in the Pleiades being pretty much the same as where they are now, although these two are a lot closer than they are now. But in any case, these were fairly far apart, and now they're much closer. And to the naked eye, it would be hard to distinguish the two stars. Whereas 100,000 years ago, it might have been easier. So the basic theory is that in the dawn of our ability to have storytelling and sentient thought and observing the world, 100,000 years ago is a long time ago in our evolution. Uh, that we developed these stories that involved seven, and later it became six due to the motions of these stars. So anyhow, I'm sure we'll hear more about this. I was joking with Gerald that this is one of those theories that can never be proven, so there will be a lot of mileage.
Yeah.
And
My favorite
but
kind of theory.
yeah, my favorite kind of theory. So anyhow, you'll hear more of these types of things, I think, as
We don't want to call them
time goes
conspiracy
on.
theories, but
Yeah,
something
yeah,
like that.
it's kind of like that, but it also has a certain amount of credibility to it.
Yeah.
I mean,
Yeah.
one of the similarities is in the Big Dipper. There's a double star, Alcor and Mizar, and when I look at Alcor and Mizar, I can't tell that it's two stars, but I do know people who can, and it's considered an eye test in parts of the world. There were cultures in the Middle East that, if you were able to separate Alcor and Mizar, you have excellent vision, and we'll put you on the team that shoots arrows. And in any case, there is some basis to observing tightly bound stars, or tightly associated stars, and then looking at them over time.
Hey, Richard, how
Yeah,
about putting that image of the Pleiades back up again?
sure, will do.
We're talking about this, and we ought to really talk about what the Pleiades is.
Sure.
The Pleiades is what we call an open star cluster, and there are quite a few of them out in the night sky. Most of them are so far away that you can't really see them with the naked eye. The Pleiades is one of a few open star clusters that we can actually see with the naked eye. In fact, a lot of people, when they see it, they think it's the Little Dipper because the pattern of stars reminds them of the Little Dipper. But actually, the Pleiades to the naked eye is much smaller than the Little Dipper is. An open star cluster is a group of stars that all formed at about the same time out of a huge collapsing cloud of gas and dust. And this is how stars form, clouds of gas and dust, because of the mutual gravitation of the gas molecules and the dust molecules. They slowly pull together and condense and begin to form new stars. So these stars all formed out of a huge cloud of gas and dust. And you can see that there's still some gas and dust in the region, although there's some debate about whether that gas and dust is actually around those stars or between us and those stars. But that is how these open star clusters form. Our sun was once part of an open star cluster like this. And what happens is the stars form. Eventually, the cloud of gas and dust dissipates, and this group of stars is left out there in space, all moving in roughly the same direction as they orbit around the galaxy. And slowly drifting apart. I like to use the buckshot analogy that they initially were very close together when they first formed in the cloud of gas and dust, but over time they begin to spread out because their orbits around the galaxy are not all exactly the same distance, so they orbit at slightly different velocities. Got some sort of a thing just now. I don't know if you heard that or not, but anyway.
That might have been me. That's an accident. Sorry.
Okay. Anyway, so they orbit around the galaxy, but because they're not all exactly the same distance away from the center of the galaxy, they orbit at slightly different velocities, and that causes them to eventually spread out and become individual stars. But they start out as an open cluster like this. John was telling us a while ago that there's at least 1,000 stars in this open cluster. Most of them are much smaller than the bright ones you see. Can't really see them with the naked eye, but through telescopes we can see them. Now, an interesting thing about the Pleiades, also known as the Seven Sisters, in Japan, it's called Subaru. And if you look at the pattern, the emblem that's on the front of a Subaru car, it's actually the pattern of stars that you see in the Pleiades. That company was formed by 6 companies that got together, they merged, and so they decided to use the Subaru emblem.
So I want to point something out. The Subaru logo has only 6 stars.
Right.
But if you find a 100,000-year-old Subaru Outback, it has 7 stars.
They're pretty reliable cars, but I'm not sure.
I don't know about 100,000 years. 100,000 miles, yeah, but years.
So anyway, another interesting thing about open star clusters, because they are all fairly close together and formed at about the same time, and they're quite distance away from us. The Pleiades is about 400 light years away from the Earth. So any differences that we see in the brightness or the color of the stars, those are intrinsic to the stars. They're not because one star is way farther than the other, or because one star has got more dust in front of it than the other, or anything like that. Those colors and their brightness are intrinsic to the stars. And by studying stars in open star clusters, we can characterize stars based on their mass and their evolution. And we learn a lot about how stars are born and how they die and how they live. And we can then use that, what we learn from open star clusters, to then study other stars that are off by themselves. And you sort of have a template that you can use because you've learned, how big a star is when it's a certain color, or how much mass it has, how bright it should appear at a certain distance, and so forth. So star clusters are really important for astronomers to use in learning about stellar evolution and learning how to characterize stars so they can study much more distant stars. All right.
Yeah, great.
We got a question. Sabina wants to know, what will the Pleiades look like 100,000 years from now? Well, 100,000 years is probably too soon. Probably needs to be more than that. It will change.
On the other hand, though, the apparent motion of Pleione and Atlas is rapid enough that I think it would be as much change in the next 100,000 years as there was in the last 100,000 years. And I would think that it's fair to assume that they will have swapped position by then.
Yep. Yep.
Yeah, but again, most of the cluster will still look pretty much the same.
Most of it will look the same.
But they are gradually drifting apart and will eventually completely scatter. But that will take millions of years.
Millions of years, yeah.
But on a related question, another one of our viewers was mentioning that her teacher at Chabot College showed the raisin bread diagram of how the universe expanded. I know what you're talking about. That's a really great analogy. That if you think of the universe as being a raisin bread and the entire bread rises, everything in the bread gets farther and farther apart, and there is no center. Everything is getting farther apart from everything else. So the notion of there being a center of the universe is explained using that raisin bread analogy. But that has nothing to do with clusters like the Pleiades.
Right.
The Pleiades is much too local an object to be explained by the expansion of the universe. And what those raisins are representing in that raisin bread analogy are galaxies or galaxy clusters and not stars inside the Milky Way galaxy.
Right. Within the Milky Way.
She said she got an F. Well, you take it again, and this time you'll get an A. Just watch our program here on Saturday nights, and you'll do fine. That's funny.
Any other questions online?
We're keeping up with them.
Okay, good.
There's some comments, but mostly comments, not questions. So
okay,
we're good.
Only nice comments.
Yeah.
Well, that's just because they don't know us.
That's right. I was just thinking that. Yeah. They don't know any better.
Yeah.
All right. Well,
so we were going to, we were going to talk a little bit about the moon tonight. The moon, and we're a couple of days past full moon, so the moon is waning gibbous. Unfortunately, again, because of the weather at Chabot, we can't point our telescope at the moon. But it's up right now. So if you happen to be somewhere where the sky is clear, get your binoculars out or get a small telescope out and go out and take a look at the moon. As the moon wanes more, becomes closer to third quarter and so on, you're going to be able to see a lot of shadows on the moon, and that helps you see the depths of the craters and how high the mountains are and so forth. It's a really great time to be looking at the moon. Full moon is a terrible time to look at the moon, but once you start getting some shadows, then you can really get a sense of what the texture of the moon is like.
Well, we got a couple more questions.
Okay.
Little V wants to know if the original star of Bethlehem was actually a supernova. Well, last week, everybody would have told you no, it's the conjunction of Jupiter and Saturn. But that is one of the competing theories. Right. So there are several theories out there of what the Star of Bethlehem story originated from. A supernova is certainly a candidate.
Yeah. Part of the problem is that there's a lot of debate about when the Star of Bethlehem actually appeared. Right now we celebrate Christmas in late December, but that was a decision made in order to accommodate another religious group that had a wintertime holiday. The evidence suggests that Jesus was actually born sometime in March. So, depending on what you believe, it's a different time of the year. And so who knows what it was,
And the whole calendar was redone between then and now.
Right.
So
it's actually been redone a couple of times. So,
yeah.
So.
All right. A couple more.
Are you getting them off of Facebook or YouTube?
I am. I'm seeing a Facebook. I'll switch over to.
I'm keeping an eye on YouTube as well. But
okay.
Okay, good.
Holly
There have been
asked,
comments.
what are the gravitational forces like, or what are the gravitational forces like within a star cluster, and are there any? And in an open star cluster, not so much. There's some, but in a globular star cluster, which we haven't really talked about tonight, but when we're back in front of our telescopes and showing you deep sky objects, we'll probably get back to the topic of globular star clusters. There are most certainly very strong gravitational forces. They are gravitationally bound clusters. So it really depends on the density of the cluster. And
Right.
Germ wants to know if that's the 36 behind me in that picture.
Yes, it is.
Yes, it
Actually,
is.
it is,
I
yeah.
am not actually sitting in front of the 36-inch telescope.
Yeah, the sky is too clear behind you.
Well, you can tell because I'm not wearing a jacket.
Yeah,
Right.
Richard, you mentioned globular star clusters. You saw the picture of the Pleiades, which is an open star cluster, and you notice there's no particular pattern to it. It's just a bunch of stars sprayed out there in or not the solar system, in the galaxy. But I got another image I wanted to share here with you. This is what Richard was talking about. This is called a globular star cluster. And this was taken with one of Chabot's telescopes. And very different. The stars in a globular star cluster are not, well, they're orbiting around the galaxy, but they also orbit around the center of the cluster. So they're orbiting in and out around the center of the cluster in highly elongated elliptical orbits. And because of that, they spend a lot of time in close to the center, and then they spread out as they get far from the center. And that gives it this kind of a globular or ball-like appearance. And that's how the name globular star cluster came. Most of these are in the region of the galaxy called the halo. And these globulars orbit around the galaxy, and the stars in the globulars orbit around the center of the globular. All right.
Yeah. Thanks.
We got a question. I was just trying to look it up. I haven't got the answer yet about the distance across the Pleiades. The basically I guess the diameter of the whole cluster, and I don't have that yet.
Yeah, I don't either. But I was reading it not too long ago, and I can't remember the number. Gosh. Well, our mission for next week.
Yeah, we'll have that piece of information for you then.
Yeah,
so tune in next week to find out the distance between the stars and the Pleiades.
Yeah.
Well, not the distance between the stars, but the total distance,
distance
across the cluster.
Yeah.
Well, you can add them up.
Yeah.
Okay.
I think that's it.
Right.
What do you guys think?
Well, I want to remind everybody once again, Chabot Space and Science Center is closed right now, so we cannot have visitors, and that means we don't get the revenue that we would normally get from people coming up and enjoying our exhibits and so on. We will be opening later on this year once the pandemic has subsided. And until then, we are relying heavily on donations and support from the public. So if you've got a minute, there's a donate button on the Facebook page right now, or you can go to the Chabot Space and Science Center website, chabotspace.org, and click on the donate button there and help us out. We'd really appreciate it. All right.
Thanks, Gerald. And thank you, Joan. Somebody just chimed in 448 light years.
Ah, there we go.
Is that
now
how
we have to
wide
find
it is?
something else next week to talk about.
Is that how wide it is or how far it is?
Yeah, we're not certain. I think that's a good question.
Yeah, because I know at one time that was roughly the distance. They've since figured out it's a little bit closer, but that was at one time about the distance that was estimated for it. So.
All right. Well, we'll figure this out. We'll figure this out and get back to you next week.
Yeah,
right.
Yeah. All right.
All right. Well, good night, everybody, and Happy New Year again. And thank you for visiting tonight. And we'll see you next week.
hopefully with the clear skies so we can look through a
Oh,
telescope.
that would be good.
Yeah, that would be
Yeah.
good. That's right.
Okay.
All right. Good night, everybody.
Good night.